I'm Lauren Hoffman, and I will be explaining rotational motion. Any object traveling under constant angular acceleration, rotating about a fixed axis, can be described by its angular position, theta, which is the distance it travels in the circle in a certain amount of time, its angular velocity, omega, which is the change in the distance that it travels over the change in time, or the angular acceleration, alpha, which is the change in angular velocity over change in time. So to get a better grasp on this, we have Nanook the dog as an example. Nanook the dog is tied to a pole on a leash. He soon becomes bored and begins running in identical circles around the pole. His motion has a constant radius of the length of his leash and a fixed axis of the pole. If he travels with a constant acceleration, he is traveling with this rotational motion that I am describing here, which can be described by a set of equations similar to those that describe motion under constant acceleration in either 1 or 2 dimensions. These equations here you can see. You can also notice that these are the same equations as constant acceleration. If you replace angular position with x position, angular velocity with v velocity, and angular acceleration with a acceleration, it's the same equation. So easy to remember. 2 specific things that you need to know about rotational movement is that a rotational axis must be specified. And also, since the object continues to return to its original position as it goes around in a circle, you have to pay attention to the number of revolutions it travels around this circle. So I have a problem to do. It's problem number 13 from the book. It says, a spinning wheel is slowed down by a brake, giving it a constant angular acceleration of negative 5.6 radians per second squared. During a 4.2 second time interval, the wheel rotates through 62.4 radians. Question is, what is the angular speed at the end of the 4.2 seconds? So we're trying to find the final angular speed here. First, we take all of our knowns. So we know angular acceleration, negative 5.6 radians per second squared. We know time final is 4.2 seconds. And we know position final is 62.4 radians. And we look through our equations and we see that if we use the equation final position equals initial position plus velocity times time plus 1/2 at squared, we can solve for initial angular velocity and further plug this into the next equation. Angular velocity final equals initial angular velocity plus acceleration times time to solve for final angular velocity. And once we plug all these numbers in, we get a final angular velocity of 3.10 radians per second.